Thank you, Ume. At the outset, I'd like to thank the organizers for giving me an opportunity to be a part of this meeting. Both Chandan and HRK have been my teachers. And with HRK, I've had this, okay, he's now smiling, wondering what I'm going to say because I've told him a little bit over tea time, so I'm not going to say anything. So I have, he's been really supportive. And even from my first semester, I've received a lot of advice, which at that point, I didn't take it as advice. But later on, as an independent faculty member, I've always called him up whenever I've been in trouble, and he's always been there supportive. And thank you. So now what I'm going to talk about is some work which we've been doing over the past few years to understand magnetism beyond the 3D transition metal oxides. Now the question is, when you examine the various examples of magnetism that one finds, usually you have magnetism among the 3D transition metal elements and the compounds which they form. And when you go beyond the 3D transition metals to the 4D, you have some examples among the ruthenides, and more recently among the 5D, you have some examples of magnetism among the iridates, where complicated spin-orbit physics is also at play. And I'm not going to discuss those aspects, but most examples, if you ask an experimentalist to take a set of compounds and try to make a 4D transition metal oxide or a 5D transition metal compound, what you'd find is you wouldn't really find magnetism in those materials. And the reason for this is very simple, because if you start with the paramagnetic density of states, which I show schematically over here, with this for the majority spin channel and this for the minority spin channel, and the Fermi level passing through over here. And so what happens is that if you have a substantial intra-atomic exchange interaction in these materials, what you'd have is that the majority spin levels would move from their position in the non-magnetic density of states. They'd move deeper into the valence band, whereas the minority spin channel are going to move up, and essentially you're going to have a local magnetic moment generated. And so what happens is that as you go from the 3D to the 4D to the 5D transition metal elements, what you're having is that the extent of the wave function of the transition metal atom also increases, and as a result of this, you have an increase in the bandwidth. And also in these materials, you have a decrease in the intra-atomic exchange interaction strength. So going back to the schematic that I had over there, what you're going to have is that this exchange interaction strength you had some levels which were here, which have moved down, and so they've gained in energy, whereas some levels which were here have moved up. And so there's been they've lost some kinetic energy in the process. And so in a perturbative scheme, you can show that the intra-atomic exchange interaction strength should be greater than 1 by the density of states at the Fermi level, assuming a constant density of states over here. So that means that if you had wider band materials, you have something which contributes less at the Fermi level, so you would require a much larger Hund's exchange to sustain a local magnetic moment. And that's why you don't have a local moment sustained in the 4D and the 5D transition metals. So if you don't even have a local moment forming in these materials, there would be no question of magnetism being sustained. So that's why it was really a surprise when in the year 2011, so many years after transition metal oxides have been, been studied, people came up with 2 examples of strontium technetium oxide and calcium technetium oxides, which had these were antiferromagnetic, and they had a Néel temperature in the strontium case, which was 1023 Kelvin, and the calcium case was 800 Kelvin. So if you go, so when I'm sticking to half filling of the band, where it's actually the spin orbit effects, because you have the T2 half filling of the T2G, the spin orbit is effectively L equal to 0. So there's no effect of the spin orbit at the half filling. And so that's, so what we have is that if you looked at if you went back to the periodic table and looked at these elements, technetium has a formal d electron configuration of D3 in these compounds, And what you have is manganese, its 3D counterpart is strontium manganese oxide, and it has a anneal temperature of 233 Kelvin. So this seems, not only do we have an example of a material which is far more, which has a higher order, which shows magnetism among the 4D, but it also has a much higher magnetic ordering temperature than its 3D counterpart. So this seemed a very puzzling result. And to answer the first question, why it took so long for this material to be synthesized and studied for its magnetic properties, was because it's radioactive. And so it required special handling facilities. And it also, that's when, you know, the theorists who don't have to worry about radioactivity literally pounced on these materials. And well, so I'm going to, so since, you know, you need special handling facilities for these materials, even simple experiments like looking at the magnetism required some unusual ways of examining it. I mean, they didn't study it to expect magnetism. What they did was they did some neutron scattering measurements, and they found that there were additional peaks in the neutron scattering, even in the most symmetric phase, which was the cubic phase. And then what they did was they examined the intensity of that particular peak, which as a function of temperature. And what they found was that they associated a Néel temperature with this material, this is the strontium compound, which had a Néel temperature of 1000 plus Kelvin. Similarly, so the question was, could it be lattice distortions which would be playing a role? Because what you have is these materials come in the perovskite structure, which we've seen earlier, but a brief recollection. You have, in these materials, you have the alkali metal atom, strontium or calcium, sitting at the center of a cube. You have the transition metals at the corners of the cube, and you have the oxygens sitting at these, at the centers of these, these edges. And so what you have, a typical distortion which you have in these materials is that the transition metal oxide, these octahedra associated with these transition metal atom tilt for various reasons, which I won't go into now. And as a result, what you have is that the angle, the transition metal, oxygen transition metal angle deviates from 180 degrees in the ideal case, when you had an ideal cube. But the most, for instance, taking the example of strontium manganese oxide, this angle is 180 degrees, whereas in the case of the calcium technetium oxide, the angle is 150 degrees. So, well, it possibly isn't the angle which is playing a role in these materials. Examining the strontium technetium oxide, looking at the density of states, what you have is that there are certain puzzling aspects which emerge when one examines the density of states. First thing is that if you were to associate a Stoner instability, you find that at the Fermi level, you have the density of states at the Fermi level is 4.3, but then it's not all on the technetium atom, which would imply a much higher J would be needed to, you have to take the component of the density of states on the technetium atom to associate a local moment formation with this. And one thing which they found was that while you explored various magnetic configurations like the ferromagnetic and different types of antiferromagnetic configurations which you could have in a cubic lattice, but they always found this G-type, which is one in which every transition metal atom has all its neighbors totally antiferromagnetic. That was the one which was easily stabilized within these calculations, whereas most of the other calculations didn't even sustain a local magnetic moment. Similarly, for the calcium counterpart, what you can see is they've explored various magnetic configurations, and the ferromagnetic is barely stabilizing a magnetic moment, even in this case. So what was special about the totally antiferromagnetic G-type antiferromagnetic configuration here? Similarly, if you looked at there were some theoretical calculations done by the WASP group people. And what you have is, they examined calcium, technetium oxide, strontium, and barium. And as a rule of thumb is that your angle is actually going all the way, is more distorted in the technetium, oxygen-technetium angle is most distorted here. It's less distorted, and it's 180 degrees in this case. This compound is not synthesized, so you don't have an experimental column over there. And they were able to map these. They did this for various magnetic configurations, mapped it on to an effective Heisenberg-like model, and then calculated a Néel temperature within a classical Monte Carlo, and they were able to get Néel temperatures in reasonable agreement with the experimental value. There are two aspects when you want to think about magnetism. One is the local moment formation, and then how the local moments talk to each other. So the localization physics governs the fact that there is a local moment at each site, and the interaction between the hopping interaction strength between the sites governs how the moments talk to each other. And so what the group of Antoine Georges and his co-workers found was that if you plotted the Néel temperature in some scaled units as a function of the proximity to the point where you're going from an itinerant behavior to a localized behavior, what you find is strontium manganese oxide lies far away from this point, whereas strontium technetium oxide is at this point where it's going from a itinerant to a localized picture, and that's why they said that it had such a high transition temperature. Indeed so, but then why don't we have other materials? And could I pick up any other example with a different electronic configuration and find a high Néel temperature associated with such a material? So this was when we decided that there are very few examples, and why is it that there are so few examples, and what's so special about only this strontium technetium oxide, which has revealed such unusual results? And ab initio calculations could reproduce this trend which was found in the experiment, but really it couldn't give us a clear picture of what was the underlying mechanism which stabilized the antiferromagnetism in this set of compounds. We first reproduced the earlier results, and indeed we found that we could stabilize the totally antiferromagnetic ground state in every case, whereas as found earlier, we had in some cases, we found that the ferromagnetic and the A-type antiferromagnetic, where it has fewer, so the number of antiferromagnetic neighbors that the transition metal atom has is 2 in this case, 4 in this case, and 6 in this case. And it seems to be that more the number of antiferromagnetic neighbors, you have increased stability in this case. So what we then did was we said, let's study it within a multiband Hubbard model and try to understand what's happening over there. And so the relevant model that we considered had the oxygen p states, and then we also had the transition metal d states hopping between the oxygen sites and hopping between the transition metal sites and the oxygen sites, as well as Coulomb interactions parametrized with taking taking the orbital character into account and taking full multiplet interactions at the transition metal site. So in order to determine the parameters, we fit the ab initio band structure to this tight binding model, the basis which I explained earlier, and we extracted out the parameters. And what you can see, there are several parameters listed here, but essentially when you go from the technetium compound to the 3D oxide, strontium manganese oxide, what you find is the relevant, since we are talking about the T2G orbitals, the relevant interaction strength to be worried about is the PD pi, and that decreases from 1.5 eV to 1.2 eV. Reflecting the bandwidth change that one usually finds. And using these parameters, we varied U, and we've also gave ourselves the freedom of varying the Hund's exchange interaction strength, as well as the delta, which is the charge transfer energy between the oxygen P and the transition metal D states. We want. Within the model, what we did was we calculated the density of states, and with a very small value of U, what we were able to do was we we were able to stabilize an antiferromagnetic ground state in this material. And this is, of course, because you're at half filling of the T2G band, and so then it's a nesting dominant. The nesting, as a result of nesting, a gap opens up even at a small value of U. What we then did was varied U and examined various solutions. And what you can see is that even when the gap opens up, your magnetic moment at the technetium site is very small compared to what you would expect for a D3 system. It's about, it's less than 1 Bohr magneton, and it increases as you make the system more localized. Now, we calculated various magnetic configurations, and again, what's plotted here is an effective a measure of the Néel temperature. So we calculated various magnetic configurations, mapped it onto a Heisenberg-like model, and extracted J1 and various exchange interaction strengths, J1, J2, and so on, and then used that to estimate to calculate J0, which is proportional in a mean field sense to which is proportional to the Néel temperature. And what you can see are two, so let's just focus. There are several things shown on this plot, and so let's just focus on this. This is the result for strontium technetium oxide, as well as the result for strontium manganese oxide, which has a Hund's coupling strength of about 0.8, whereas in the strontium technetium oxide, we expect the Hund's exchange, Hund's coupling to be about 0.3 eV. And so indeed, what we can find is that taking a U of about 2 eV for strontium technetium oxide and a U of about 3 eV for the strontium on manganese, we can get the kind of we can get the correct ratio of the Néel temperatures. But what's most surprising is that you have what it predicts is that for the 3D oxide, for the 4D oxide, what you have is you have the Néel temperatures lying on this curve over here, much higher than the 3D counterpart over here. And so you have, we also get this regime of where in this regime you have the super exchange regime where the Néel temperature, if it's dominated by the first nearest neighbor exchange interaction strength, would vary as 1 over U, and we have that dependence. And in the low U regime, we have a dependence which is almost increasing linearly with U. And so you have this peak. So what is it which gives us, so this also, the smaller, what's surprising is that the smaller Hund's exchange interaction strength material has the higher Néel temperature compared to the one which has the higher JH. And this can be easily understood because what we are looking at is a half filling of the T2G band. So if you take one technetium transition metal site, suppose you have the downspin occupied at that site and the upspin totally empty, and at the neighboring site you have the upspin occupied and the downspin completely empty. Then because it's a half filling and your Fermi level is over here, what you can have is there's hopping between because of super exchange interactions, what you have is you gain maximally when you're in the antiferromagnetic configuration. And this is why the G-type, totally antiferromagnetic solution is the one which is stabilized in all the calculations. And the two factors which determine the effective exchange interaction strength are the hopping interaction strength, and the scale of JH actually determines the separation between these levels. So both these actually end up aiding the super exchange interaction and therefore increasing the Néel temperature in these materials. We could also use our extracted JH, extracted exchange interaction strength in a classical Monte Carlo, and what we did was the blue dots over here are the experimental values of the magnetic moment variation as a function of temperature at a given at one technetium site. Remember, it's an antiferromagnetic system, but you could look at the variation of the magnetic moment at a single technetium site, and we could get the same dependence within our model, suggesting that and as well as the correct value of the of the Néel temperature. So this mechanism seems to be generic to all the D3, all the compounds which have the same half filling of the band. And so are there other examples? So we worked out a phase diagram because all the properties of the transition metal compounds are essentially determined by the charge transfer energy and the scale of the U. And so what you have is you can, depending on the U and the delta values, you could have various examples of high Néel temperature compounds over here. Considering another which hasn't been identified in the same class of materials, we looked at sodium osmium oxide, which again is a 5D oxide, and what it has is a Néel temperature which is surprising for a 5D oxide. It's about 410 Kelvin, and it's also said to be the first example of a Slater insulator. And to remind you what a Slater insulator is, it's a material in which the insulating state has its origin as the magnetic ordering Okay, so what you have is that you have a metal insulator transition taking place over here, and if you look at the magnetic transition, it happens at exactly the same temperature. Looking at the structural data, one finds no volume change, and so there is no structural transition associated with this metal insulator transition, and that's why it's believed to be the first example of a Slater insulator. And we believe that the same mechanism is operative in this material, and we did the same kind of analysis, looking at various magnetic configurations, building up a multiband Hubbard model, and then examining the multiband Hubbard model within our calculations. And what we found is that, well, if you had the sodium, if you had the 5D oxide here, or somewhere here, then you have the 4D oxide here. So so whilst sodium osmium oxide could lie on the rising part of this curve, and that's why it has a smaller Néel temperature than strontium technetium oxide. You could find some other osmium compound which could be much higher and therefore have a much higher Néel temperature than even the 4D oxide. So you could realize a much higher ordering temperature in some other example. Well, so far so good. So what we've seen is that we can understand what is it, the route to high magnetic ordering temperatures among these 4D and 5D oxides, and it's found to be a generic feature of the half filling limit. So now, so we say, okay, since the nesting mechanism seems to be playing a very important role in the insulating state, let's see whether this magnetism survives when we are doping, when we are carrier doping this limit. And so, and there's also a lot of recent interest into this class of materials which could be active components for antiferromagnetic spintronics. And for those of you who are interested in this field, if you open today's ConMat, there are at least 4 or 5 papers talking all about antiferromagnetic spintronics. And what one is looking for are materials which could be, antiferromagnetic metals which could be spin injectors or electrodes of a magnetoresistance device. And people say that these materials could be far more, the antiferromagnets, because they have no stray fields, could work far more efficiently. Of course, most of these are theoretical predictions, and so one should examine these claims more carefully. So anyway, so what one usually associates associates a metallic ground state with ferromagnets, whereas you always have antiferromagnetism accompanied by an insulating state. So antiferromagnetic metals are quite rare, and especially if you look around among the transition metals, you have chromium as an example, where nesting is believed to be the mechanism by which chromium has this unusual antiferromagnetic ground state. But you have very few other examples, especially among the transition metal oxides. There have been some numerical work which suggests that there is, that suppose you, these are numerical works that have on a two-dimensional Hubbard model. So if you go away from half filling where you have an antiferromagnetic insulating state, if you dope carriers into this, you could possibly realize an antiferromagnetic metallic ground state, and this is what we wanted to explore. But if you take any of the phase diagrams of the 3D transition metal oxides, what you find is that you don't find an antiferromagnetic metallic phase at any doping concentration. Usually the metallic phases are found to be ferromagnetic. And of course, it could be that one reason for this could be that you have strong electron phonon physics playing a role which modifies the phase diagram considerably. But then, then that means that our 5D oxides are a very good candidate because you don't expect electron phonon physics among the 5D, in the 5D transition metal oxides. And this is what we wanted to explore. And so we took the case of the sodium osmium oxide. We took the multiband Hubbard model, which we set up for this case, and introduced, when we introduced we did 25% electron doping in this case, and examined the phase diagram as a function of the U. And what we find is that for small values of U, we indeed have an antiferromagnetic metallic phase stabilized, and for larger values, the doped electron gets localized, and what we seem to have is a charge-ordered insulator. And unlike what we have in the one-band picture, we don't have a ferromagnetic state at a high value of U in this case. So the way we can understand the antiferromagnetic metallic phase that gets stabilized is if you look at the schematic diagram. What you have is at one site you have the T2G minority spin fully occupied, and the doped electron goes on into the other spin channel. And in the fully polarized limit, this electron would have no delocalization pathways because it's the opposite spin which is over here. But what you have is that in this very strongly itinerant limit, if you examine the density of states, you have, the blue line is my majority spin density, T2G density of states, and the red line is the minority spin channel. And so it's not totally fully spin polarized. It's something like this schematic which is shown here. You have some weight of this spin, majority spin over here, and similarly you have some weight of this. This happens in the itinerant limit as you're going to the fully polarized limit. And so this electron still has some delocalization pathways still available for it. And as a result, for small values of U, you have the D-type antiferromagnetic phase, which is stabilized. And as you increase the U, this electron gets localized, and then you have this charge-ordered phase, which is stabilized. And as we increase the dopant concentration, electron doping concentration, what we also found was that, again, the phase diagram remains essentially unchanged, except for this, energy stability associated with each of these phases is reduced. And that's understandably so because you're doping electrons into it and you're decreasing, therefore, you're doping electrons, and so it's doping electrons into the minority spin band, and therefore decreasing the effective contribution of the antiferromagnetic background, of the G-type antiferromagnetism that one has here. Now, the surprise was when we looked at the 3D transition metal oxide, we haven't included any electron phonon physics here, but if you looked at the same electron doping concentration over there, what you have is you have an entirely different phase diagram. The metallic phase is found to be a ferromagnetic metal, so at large values of U, you again recover what we had there, which is the charge-ordered insulating state. And this can be essentially understood because what we find is that the Hund's coupling is playing an important role in determining the determining the order of states which are occupied, and over here it's the doped electron goes into the EG level, which favors a ferromagnetic ground state. So what we find is that it's actually the Hund's, so it's a surprise, it seems obvious when we think about it, but it's not been, it's not been realized before, that the Hund's exchange interaction is also found to play a role in determining the nature of the magnetism in the metallic. Yeah, this is doped, 25%. Same doping percentage because it's going into this one. So it's going to the EG level. So therefore it favors a ferromagnetic ground state. Okay, I'll just show you one more result. A CW paramagnetic, because we find various solutions which have same energy. So I mean, various magnetic solutions have pretty much similar energy, and so we call it a Curie-wise paramagnet. So now, when we had more surprises, okay. Oh yeah, okay. So one other aspect is that in all these cases, we had all the d orbitals at each transition metal site, but we did the same calculations with a single band with a single orbital at each transition metal site. What we have is we recover the large U limit, and we recover ferromagnetism in contrast to what we find here, which is a charge-ordered insulating regime over here. Another aspect which seemed which seemed a little intriguing was that when we hole doped, what we found was that the phase diagram didn't change so much for the 5D transition metal oxide, and this is again, I think, 25% electron doping. And what we find is the G-type and 12.5 is shown in black, and the 25% is shown in red. And what we find is that the G-type antiferromagnetic metallic phase is stabilized over a much wider U range in this case, but the types of phases we find are similar. But then in the 3D oxide, when we look at it, what we find is that at the 12.5% doping, we have no metallic phases. Maybe we have only the non-magnetic metallic phase, but at the 25% doping, what we have is we have the C-type, we have an antiferromagnetic metallic phase which is stabilized over here. There's a strong asymmetry, and that's because you're doping, in this case, you're doping into the T2G band, and it has possibly a smaller hopping interaction strength, and so the gain by super exchange is much less in this case compared to in the case of the EG, electron carrier going into the EG orbitals. So essentially, we have a different phase. We have a strong asymmetry on doping in the case of the 3D oxide, which is not there and not present in the case of the 5D oxide, and this is determined by the character of the whole state. And finally, I'd like to conclude by the people who've actually carried out these works. The undoped compounds were a work of the PhD thesis of SrMnO3, who's actually an experimentalist, who, while waiting for some of his samples and experimental facilities, carried out this work with me. And the doped transition metal oxides work is part of Shishir's thesis, and these are the published references, and it's done in collaboration with TD. Thank you for your attention.
Priya, we have time for questions, comments.
I wonder if you could just go back to the foil that had the buckling angles.
Yeah.
For the 4D and 3D. I didn't catch it.
Maybe I'll go
way back where you had the.
It's easier to do it from there.
Just a simple table, 2 rows, 3 columns. So the manganese, oxygen manganese, you mean it's a straight bond?
It's a straight bond, yes.
Whereas the other one is buckled?
Yes.
Now that's what you'd expect for the T factor, because the RBO in the denominator of the T factor has got,
Yes, yes, yes.
because the
Exactly. The tolerance has, yeah, the tolerance, it's because of the tolerance.
smaller.
Yeah.
So could that
That would have, that would decrease the super exchange. But then, okay, but we're talking about different hopping interaction strengths because the PD, the relevant hopping, the PD pi in this case is much larger, is about 20% larger. That's what I showed you.
I mean, if it was just a matter of, I realize this is too simplified. If it was just bandwidth versus U,
Yeah.
then buckling it at the same U would make it more magnetic.
It wouldn't make it more magnetic because because the coupling is reduced, so the coupling depends on the super exchange. So if the effective T between the sites is reduced, the super exchange is.
Yeah, this is a more too trivial. Okay, I realize what you're saying.
Any other questions or comments? Yeah, by the way, technetium is not only radioactive, it's the least abundant element on the Earth.
Okay, okay.
Which is why it's not.
Okay, okay, okay.